In this lesson, we're talking about linear functions. So let's first talk about domain, right? This set of inputs or x coordinates. That's our domain. The range is a set of y values, or also known as outputs or y coordinates of order pair. A function is a relation in which each element domain is paired with exactly one element of the range, right? A function is when all the x values are unique. That's what we consider a function. Here's a new notation. Function notation. So when it's a function, how do we write it? In function notation, f of x is read as f of x. So if you see this notation there, we read that as f of x. Yeah, very important. This does not mean f times x. This is f of x. X represents the domain or input value that is substituted into the function. So like right here, that x, that's our input function, our x value. It's our domain, right? The result of evaluating that function is the range or output. So the f of x is the range. So f, and by the way, f of x is equivalent to the y. F of x, g of h of x, all those are just y. So it's very important. X and f of x, right? X is domain, the input. F of x is kind of like a y. It's the range or the output. Instead of kind of like the y, it is the y. It's like another name for the y. It's the y dressing up, right? So f of x is just like a y. G of h of x, they're all just the y values. X of which you're plugging in. Okay. So when you see a function notation, when you see an equation like this, that's a function. Y equals 5x plus 1. Another way to write this, like we just talked about, is writing it f of x equals 5x plus 1. Right? So same concept, right? This is our function. X is our input, so that's the stuff we're going to plug into it. That's our domain. Y is our output. Same thing here, right? X is our input or domain. Y is our output or range. So a lot of times you'll see people write this as like a function machine. It's just a way to visually represent what's going on. Because really all this function is, this 5x, it's just a rule. It's saying, hey, whatever x is, times it by 5 and add 1. That's it. That's what it's trying to tell you. Whatever x happens to be, times it by 5, add 1, that's your y. The beauty of functions is that we can use it to find a relationship between variables to solve problems and to make predictions. So it's a very helpful mathematical tool. So this is an example right here. So you'll see this like function machine people like to use. So here's our domain, here's our input value, right? Whatever x happens to be, and what we're gonna do is it gets plugged in for the x, or substituted in more correctly for the x, right? And then whatever that turns out to be, that'll give us our answer, our f of x, or y value. That's the range. So we plug in the domain, we get our output, our range, right? That is our function 5x plus 1. So actually, let's actually do a problem with it. It's over here. So we have our function 5x plus 1, and what's going to happen is that we want to find the value when x equals 3. So all that means is, like for a function right here, I always think about it like this, right? G of x is equal to 5x plus 1. All this is really saying is g of something is equal to 5 times something plus 1, right? People get caught up in the fact that it's an x. X is just a placeholder. In this case, x is going to be replaced by 3. We're going to plug 3 into there. So we're going to have g of 3, which is telling you, no, hey, substitute 3 in for the space, right? For the x, that's all it's saying. Substitute, plug 3 in. That's all it's trying to tell you. So it'll be 5 times 3 plus 1, and then 5 times 3 is 15. So 15 plus 1, so you get 16. So you'll see g of 3 equals 16. And then I always see people like divide by 3. That's when I'm like, what are you doing? This is just letting you know. It's like a sentence. G of 3 equals 16. When you substitute in 3, you get 16. So that's your answer, right? Same thing can be done with this function machine here. When you have the 3, you're going to substitute it in for the space or for the x. Then we get 5 times 3 plus 1, which is 16. That's what gets plugged out, right? And that's a coordinate point. We substituted in the 3, and we got a 16. And our answer is a coordinate point. So that is our answer. Okay, let's do a couple examples here. Evaluate each function for x equals 4. So we're going to substitute in 4 for all our x's in these two problems. So this first one here, right? We want to figure out what g of 4 is. So in here, right, all we're going to do is we're going to change that x. So instead of being x, it's now going to be 4. Everything else stays. Then we do order operations. Negative 2 times 4 is negative 8. Minus 3. So we get, remember they're both negative, so like you went back 8 and then you go back another 3. So negative 11. That's what g of 4 is. Again, that's just your answer. All this tells me is when you substitute in 4, you get a negative 11. That's it. Okay, this one, same idea. We're also substituting in 4. So it's going to be h of 4. So that's just going to be 7 times 4 plus 15. So 7 times 4 is 28 plus 15 would be 43. That'll be our answer, right? Or h of 4 equals 43. So that's the idea. Okay, that's how you evaluate a function. Next, let's talk about how we write a linear function. Now, we did this before. We generally 2 ways to write a linear function. Way 1, or method 1, is we're going to use y equals mx plus b. Right? You have to find your m, your slope, and you have to find your y-intercept b. Way 2, my favorite way, is you do y minus y1 equals mx minus x1. Right? In this case, you have to find your m, and you have to find your x1 and your y1 point, which could be any point. So in this example here, the cost to make 4 bracelets is shown on the table. So here's our table, and it says you make 1 bracelet costs $17, you make 2 bracelets cost $32, 3 costs $47, and 4 equals 62. So step 1, if you notice on both of these, I have to find my m. So how do we find the slope? Right? We could use the formula y2 minus y1 over x2 minus x1. We do have 2 points here. You can also use the, remember that slope is also rise over run, or the change in y over the change in x. If we look here, look at the change of y. 17 to 32 is 15, and it's constant 32. 47 is 15, 47 to 62 is 15. So our change in y is 15, and our change of x is 1. It just changes by 1 every time. So our slope is 15. Now again, I would have got the exact same answer if I did y2 minus y1 over x2 minus x1. If I used these two, it would have been 32 minus 17 over 2 minus 1. So whatever you feel more comfortable with, right? So you could do change in y. As long as it's constant, that's just your change of y. This would be my change of x. You're just doing slope in lots of different forms. So that is my slope. The fact that it's a constant rate of change means it is a linear relationship. And then right here, they show you how they did way 1, right? If I'm doing way 1, I have my slope, you plug it in. Now I have to find my b. How do you do that? You find a point, and you plug it in for your x and your y, which again, remember, f of x is your y. So in this case, they use 1 and 17. And then once they do that, you solve for b. So 1 times 15 is 15, minus the 15 from both sides. You get b equals 2, and then you rewrite it, and you get f of x equals 15x plus 2. So that's one way to do it. If we're going to do my way here, right, slope-intercept form, the easiest way to make equations, our slope is 15, and we have to find a point. You pick any point you want here. We'll pick 1 and 17. So we get y minus 17 equals 15x minus 1. And then if I want to put in a slope-intercept form in function form, which is slope-intercept form, I have to get y by itself. So we're going to distribute that 15. So I get y minus 17 equals 15x minus 15. Right? 15 times x is 15. 15 minus 1 is 15 times negative 1 is negative 15. And then we're going to add the 17 to both sides. Right? We're going to get this by itself. So we get y equals 15x plus 2. Right, so 2 different ways of doing the same thing. You could do it slope-intercept form and find the b yourself, or you could do it in point slope form and then rewrite it. Okay, let's try one ourselves. So if I was going to do this one, right, I'm going to use my favorite way, y minus y1, m equals x minus x1, right, point slope form. All I got to do is find my m, my slope, and then pick a point. Now again, we have a table here. I'm already going to pick a point, 1 and 1. Like that. Again, if you want the slope, you could do slope-intercept form. I should say you could do the slope formula if you want to find the slope, y2 minus y1 over x2 over x1. We're just going to do change in y over change of x. This will keep it simple. So this changes by 3 every single time. So that's my change in y. And this is changing by 1 every single time. So that's my change of x. So I get 3 over 1. So y minus 1 equals 3x minus 1, like that. And then again, if I'm doing a function, I want to get y equals. So I have to distribute y minus 1 equals 3x minus 3. And we're going to add 1 to both sides. So I get y equals 3x minus 2. And that is my function. Okay, let's talk about analyzing a linear function. So in this example, Tamika records the outside temperature at 6 a.m. The outside temperature increases by 2 degrees Fahrenheit every hour for the next 6 hours. If the temperature continues to increase at the same rate, what will the temperature be at 2 p.m.? So what we want to do is write an equation for this, and then we could substitute in the value to find out our temperature at 2 p.m. Right? Once we get an equation like this, then we can find out any value we want. That's the power of equations. So let's write a function. So we're gonna write y equals mx plus b. So we're doing these linear functions. Remember, when we write in this form, m is our slope, also known as the rate of change. B is our y-intercept, or initial value. Right? When we're talking about like application problems, we want to think about this as a rate of change, and then this as initial value. So first, what's our initial value? The temperature at 6 a.m. Right? That's when we're starting. What's the temperature at 6 a.m.? Well, they tell us here in this picture is -3. That's the temperature at 6 a.m. That is our B. So this is going to be -3. What's our slope? Well, it's the rate of change. What's changing here? The outside temperature increases by 2 degrees Fahrenheit every hour. So our rate of change is 2, right? If I put fancy degrees per hour, right? 2 degrees Fahrenheit per hour. We'll just put a 2 for now. But that's like the units. So there's our equation. Y equals 2x minus 3. Now, if they want us to sketch a graph, which the next one says, we make a little table. 1, 2, 3, 1, 2, 3, 4, 5. So x and our y. In this case, x is what are we talking about, right? X is time, right? 6 a.m. So this is time. This is degrees Fahrenheit. So this is like my temperature. And we're going to start at -3, my y-intercept. My slope right here is 2 over 1, right? This is my y-intercept, which is always our first point on the y. Slope is 2 over 1. It's a positive, so we're going to go up, and then we're going to go to the right. So from this point here, our y-intercept, we're going to go up 2, and right 1. So right there. And there is our graph. Next question. Find the value of y when x equals 8. So why we're doing this, right? First of all, why we're at 8? Because remember what they wanted. They wanted we started at 6 a.m. They want to know what the temperature is at 2 p.m. From 6 a.m. to 2 p.m. is 8 hours, right? 6 a.m. to noon is 6 plus another 2. So that's where we're going to find out the value when x equals 8. Now, if I wanted to, if my graph was nice enough, I could just go to 8 on my x and then figure out where it hits the graph. My graph doesn't go that far. So that's okay. Let's use our equation, right? So y equals 2x minus 3. And now we're going to substitute in x equals 8 for x, right? Use a little function notation, little functions. So let's substitute in x equals 8 there. So you get y equals 2 times 8 minus 3. 2 times 8 is 16. So 16 minus 3 is 13. And we're talking about degrees, so this is 13 degrees Fahrenheit. That would be the temperature at 2 p.m. If you notice, our function here is a line. That makes it a linear function. So that's the vocab for a line. Like a function that's a line is called a linear function. And that's the lesson.